Hello! We introduced the complementary slackness conditions last time. The CS conditions of a LP and dual is that either a variable is 0 or its corresponding constraint is tight. And the CS theorem is that if we have x bar y bar feasible for P and D, then x bar y bar are optimal for P and D if and only if x bar y bar satisfy all CS conditions. In this lecture, we will try to link CS conditions with simplex. Remember that simplex works with LPs in standard equality form. Max C transpose X, AX is equal to B, X is at least 0. The dual of this is min B transpose Y, A transpose Y is at least C. The goal here is to answer the question, what is simplex doing with relations to CS conditions? We will look at an example. We have a linear program in canonical form on the left. The basis feasible solution is 00891 with basis 345. After one iteration of simplex, we get something on the right, which is an optimal canonical form. And the basis feasible solution here is 20035 with basis 145. The main observation that will be useful for our discussion here is the placement of the zeros in the objective function and in the basis feasible solutions. Recall that in the objective function, the coefficient of basic variables are zeros. And in the basis feasible solution, the value of the non-basic variables are zeros. This means that throughout simplex, each variable I is either 0 in the basis feasible solution or 0 in the coefficient of the objective function. Notice a minor link to the CS conditions. The first parts here and in the CS conditions are the variable is 0. Now, let's look at what it means to have a 0 in the coefficient of the objective function. Let's recall the objective function in canonical form. It is C minus y bar transpose A times x plus y bar transpose B, where y bar is equal to AB minus transpose CB. So then, having 0 in the coefficient of xi implies that Ci minus y bar transpose AI is equal to 0. This implies that y bar transpose AI is equal to 0. Or, taking the transpose on both sides, we get AI transpose y bar is equal to Ci. And this essentially means that the ith dual constraint is tight. So what we have here is that in simplex, either xi bar is equal to 0 or the corresponding dual constraint is tight. So CS conditions hold throughout simplex. But this does not mean that x bar y bar are always optimal throughout simplex. Certainly, it does not make sense to have optimal solutions throughout the algorithm. But can you explain why satisfying CS conditions here does not always mean that it is optimal? And the reason is that y bar could be infeasible. Let's look at an iteration of simplex. It starts by picking a variable xj with positive coefficient in the objective function. This implies that Cj minus y bar transpose Aj is greater than 0. This implies that Aj transpose y bar is strictly less than Cj. But the dual constraint is Aj transpose y bar is at least Cj, so this is infeasible. So picking an entering variable is equivalent to finding an infeasible dual constraint and try to fix it. Simplex ends when all the coefficients in the objective row are non-positive, meaning C minus y bar transpose A is at most 0. This implies that A transpose y bar is at least C, so y bar is feasible for the dual. So simplex ends when we have a feasible dual solution. Take a look at this example again, with its dual on the right. In the first canonical form, we can calculate the associated dual solution y bar, which is 0, 0, 0. We can check that this vector is infeasible for the dual. The first constraint is violated, and this corresponds to the first entry of the objective function being positive. After running one iteration of simplex, our new y bar here is 3/4, 0, 0. And we can check that this is actually feasible for the dual. This corresponds to having a non-positive coefficient vector in the primal. So we have an optimal solution. So a quick summary here. Optimality of x bar y bar involves x bar feasible for P, y bar feasible for D, and x bar y bar satisfies CS conditions. And throughout simplex, 1 and 3 always hold, and simplex works towards satisfying 2. Once condition 2 is achieved, we have optimal x bar and y bar. Note that many optimization algorithms are based on the idea of keeping 2 of the 3 conditions true at all times and work towards the third. We will see an example later with the shortest path algorithm. Finally, as an exercise, try to show that throughout simplex, x bar and y bar have the same objective values. That is, C transpose x bar is always equal to B transpose y bar. And of course, this does not mean that they are always optimal. And that concludes our discussion on the links between CS conditions and simplex.